Hi everybody, my name is Todd.
My name is Mamaril.
I'm Kari, and today we will be enlightening you about wind power.
So, what is wind power? Traditionally, when you think of harnessing the wind, maybe even the other term, getting the kinetic energy from the wind, usually you think of when you're in the country, you see a wind turbine, or when you're at sea, you see a sail, or maybe something simple like just a kite using the wind as its energy. So, what is the history behind when we first started using wind energy? Well, there's a few stories about around 5000 BC by the Nile River. It was rumored a person noticed just the wind, then attached a little sail to a pole and caught the wind and used it to sail the river. Then by the 11th century, windmills started being used majorly just to produce food, like grind grains. And then the merchants and crusaders of that time eventually brought their technology westward towards Europe. Then it was eventually used there too. So, what is a turbine? Turbines use the energy from the wind, usually the kinetic energy, and then turn that into mechanical energy, where they turn it into energy for us to use through power. There's two different categories when it comes to categorizing turbines, known as the horizontal axis wind turbines and the vertical axis wind turbines, respectively. So the first of the two types that I mentioned earlier, the horizontal axis wind turbine, known as HAWT, there's two different types. The first is the upwind horizontal axis, which is what you mostly see, where it has to face towards the wind. It uses a yaw mechanism to be able to face towards the wind. Its axis of rotation is also parallel to the ground. The downwind horizontal axis wind turbine, this one isn't as common, and it doesn't need a yaw mechanism because the wind pushes it towards the opposite way, which it's going with the wind, so it's going the opposite direction, so the wind pushes it that way, so it doesn't need a yaw mechanism. And that is the clear difference between the two, with one facing towards the wind and one facing away.
Horizontal turbines, HAWTs, are typically either 2 to 3 blades. They are created with an aerodynamic curvature that allows the lift force to turn each single rotor blade. It's very similar to how an airplane flies. When there's airflow, the winds are exposed to both the upper and the lower portions of a blade, and this will allow for air to pass through the top more quickly than it would the lower portion, which allows the lower portion to produce a low pressure area on the top side. Next, they're highly reliable. Because these horizontal turbines are more of a standard, a lot of research and development have gone into this. Let's talk about the height of these things. They're huge. Sometimes blades itself are 70 meters and they're as heavy as 20 tons. So just by the height of these, more altitude is going to equal more airflow. And because they're generally so tall, they're going to reach a consistent amount of wind. No trees, no buildings blocking their area. Thus, they have optimal performance as well as consistent energy source.
The second of the two categories would be the vertical axis wind turbines, also known as VAWT, and there's two different types of wind turbines, with the first being called
Ceruse,
and the second called
Savonius,
the first of the two being called the
Ceruse,
wind turbine, which uses thin blades called the curved aerofoil blades to catch the wind The second of the two being called the
Savonius.
wind turbine, where it uses half circular cups to catch wind and rotate with the wind, of course. It's probably the name of the one first made by James Blyth in 1897, where he made the first wind turbine.
As you can see, these vertical turbines come in several different styles. And unlike the horizontal axis, these turbines are omnidirectional, meaning that they don't need to be adjusted to the point of the wind in order to operate like the horizontal axis turbines do. Something great about them is this type of turbine can be installed in lower altitude. They can be installed at ground level cities or even on top of an apartment building. Because of these factors, their maintenance work are definitely a lot easier than they would be for horizontal axis. They are very compact size, so they're very suited for areas where they have tall buildings, and they're much more compact. On the flip side, where they are able to withstand rough weather, they have no chance when it comes to strong winds. They will simply stop working and the blades will fall. It will literally fall apart. They aren't suited for areas with strong wind. Granted, they are best for in the city.
Rather than delay too much, let's just jump right into it with our lovely equation of 1/2 P times A times V cubed. You may guess, based on your geometry or physics knowledge or chem or whatever, that P is pressure, A is area, and V is velocity, which you may be right. But what I'm hoping you understand is that this looks very similar to our kinetic energy equations, which is exactly what it is and where it stems from. You know, our 1/2 mv squared, 1/2 kx squared, 1/2 I omega squared. This is how we calculate the total energy within wind at a pressure P in a Pascal units, which is Newton per meter squared, typically around 1 to 1.2, at an area of pi r squared. This is area of pi r squared. This is specific for our windmills. If you think of the horizontal axis windmills that you've seen, the tip of them trace out a circle, and that circle has a radius r, which is generally just the length of the windmill blade plus the little circle axis in the middle, which is negligible for our equation, but we'll go over that later. And that is how we calculate the area. It's just the sweep of where the wind is. And then, of course, this wind is moving at a velocity. That is what is pushing our windmill. And that term is cubed here. There is a derivation for this formula, obviously, but I won't be going over that because that's kind of a little too much time for us at the moment. But just know that our big players in this equation here are the velocity and the radius. The Pascal, as I mentioned, is about 1 to 1.2, so it really doesn't have too much effect on the outcome of this equation. It doesn't scale it as hard as our r squared term, so we really want a big windmill to sweep more area, and that'll scale up our potential power. And then the velocity is cubed. That is ridiculous. So we get some really fast winds. We can expect a lot of power. And that's, just kind of what you expect of kinetic energy. The faster something is moving, the more energy it has. And so the more energy we can capture from our example here. This is kind of like an example using averages here. So I told you about the 1 Pascal, and that's just what I'm going to use. It's 1 to 1.2 on average. I chose 1, it's easier to calculate. And then we have 2500 pi. So I told you that we calculate it using pi r squared. So the r squared is 2500, which stems from 50. And this is in meters, by the way, I should note, sorry. So 50 meters is a typical radius for a windmill, which is ridiculously long. That is a huge, huge windmill, but that is exactly what windmills are. They're massive, and we want them to be massive because we want to get as much power as possible, right? But what seems small is the 6 meters per second for the velocity. And we've all experienced some massive wind speeds, but those don't happen all the time. And so what I chose for this equation is about an annual average for some typical areas that windmills are built is 6 meters per second squared, 6 meters per second, and the term is cubed. But 6 meters per second is a pretty good average. You know, we are not expecting windmills to be operational all the time. Obviously, wind isn't blowing all the time, but it's also not blowing super duper fast all the time. So we kind of need to look at the average to kind of get a feel for what we can expect. And what we can expect, oops, sorry, I went back there, is 141 kilowatts of power, which is a ludicrous amount of power. That is ridiculous. Keep in mind, this is not some sort of rate. This is just within an area at wind blowing at this speed. This is kind of the power that is stored within it. But the problem with that is, we're not operating at 100% efficiency, right? I'm sure you can guess where this is kind of going. And what has been calculated as the limit of windmills, peak windmill, your engineering is amazing and the conditions for it are just lovely. We can really only expect 59.3% of that power within the wind to transfer to our windmills. And you can sort of understand it a little bit. There's obviously inefficiencies within just the engineering, but just understand the physics of the windmill. Wind is blowing on the blades. And so obviously the wind is transferring energy to the windmills to spin it. But the windmill blades themselves have to do work on the air that they're pushing out of the way to keep spinning. So there's a lot of inefficiency there. And there's also just some other things like friction, stuff we can't avoid. And so it's sort of sad, but this 141 kilowatts of power turns only to 83.83. And again, this is not a per hour sort of thing. This is no rate. This is just kind of what is within this wind. But again, this looks pretty good. This is a lot of power, right? Except for in actuality, our windmills are only about 20% efficient.
For a brief history within the United States, because of the oil shortages in the 1970s, they dumped a ton of money into research and development of alternative methods of getting energy, like wind energy. By the early 1980s, thousands of wind turbines were installed in California, majority in the
Altamont, East San Diego County, Pachia, Solano, San Goronio, and Tehachapi
areas.
Let's narrow it down a bit. How do we use wind power? It's not like I have a windmill in my backyard. Well, locally, many of us actually use Puget Sound Energy, and PSC actually has 3 facilities within the state of Washington that operate with wind power. So, in reality, we probably have some wind power impact. We probably use their energy.
Sadly, windmills are not that efficient. They're not that great. The conditions for them are not always wonderful, and they're really hard to maintenance. These things are massive. Tons of things can go wrong, and if winds blow too fast, or maybe bad weather, like rainstorms, tornadoes, where you expect high wind speeds, you also expect disasters like tornadoes. It's hard to maintain windmills.
Where we may have used windmills and turbines for centuries in some form of way, it is not the most beneficial. And where we have re-engineered and redeveloped many times, where you can tell from horizontal turbines to vertical axis turbines, they're very different, but they're used for many different things. Well, wind power is very versatile. We use them in our sailboats. Even the fan that keeps us cool on a hot summer day, that's wind power. Where we might not have conducted it perfectly, there's still lots to do. So you tell me, what do you think would be a better option for wind being a powerhouse? How can we bring such a great power source in sourcing our everyday lives in a better way? What do you think?